Now, on this example that we just did, the technique of looking at the difference quotient and taking a limit as h goes to 0, obviously that took a long time. That took a lot of algebraic manipulation. So a lot of the rest of the chapter is going to be looking for faster ways to look for derivatives. So we want faster ways to look for derivatives. Well, there's a number of things you could do. One is you could just say, well, we know that the derivative is what happens when h gets really close to 0. So we could approximate the limit using some really small value of h. So we could just take the difference quotient at a really small value of h, and that would be a pretty good approximation for the derivative at a certain point. So our function f of x is equal to x squared plus 3x minus 2. We want to find the derivative of f at x equals -2. We have done this earlier using the limit of the difference quotient. In fact, we did this earlier and we came out with a -1 as our derivative. So what we're going to do is we're going to, instead of taking the limit of this difference quotient, what we're going to do is take the difference quotient with a really small value of h. Maybe I plug in, for instance, an h of 0.01. If I do that, that's going to give me really close to the limit as h goes to 0. Now, if we do this, I want to just say, for the record, h is -1. So if I do this, in the numerator, -2 plus 0.01 gives us -1.99. Then we're going to be subtracting f of -2 and then dividing by 0.01. If I plug in -1.99 into my function, I know you all can do that. Plugging that in gives me a -4.0099. Plugging in -2 into my function gives me a value out, an output, which is -4. And I'm still dividing by 0.01. So my fraction becomes -0.0099 divided by 0.01, which is -0.99. So we can approximate the derivative and say, well, the derivative is pretty close to -0.99, which we found earlier it is. Notice this takes a lot less time than going through the limit of the difference quotient. So it's a very efficient way, although it's not a very precise way. If I wanted to make it more precise, I could use a smaller h value, like 0.001. Or I could combine that by plugging in a -0.01 and a positive 0.01 and kind of looking at somewhere in the middle. Turns out if you plug in a -0.01, you get -1.01, I believe. And so you could say, well, in between there is -1. So when we look at this, we can always approximate using small values of h. It doesn't give me the exact derivative, but it gives me something that's really close. So that's one faster way to look for a derivative. We get an approximation fairly close. Another method we could use to find a faster way to look for the derivative is to do lots of derivatives all at the same time. So let's say we wanted to find a derivative at a value of c, but not just at one value of c. Let's pretend I wanted to find it at lots of different values for c. And I kind of did that with an earlier function. We've dealt with this function f of x equals x squared plus 3x minus 2 a lot. We've found the derivative when x was 2. And we also found the instantaneous rate of change when x was 1 of this function. By the way, instantaneous rate of change is just another word for derivative. So we found the derivative when x is 1, and we found the derivative when x was 2. Well, what if I wanted to find the derivative at lots and lots of values for x? Not just 1 and -2, but also at -3 and -4 and 15 and 10. It would be nice to find the derivative for an arbitrary value of x, and then I could just plug in different x values. Well, that concept is the concept of the derivative function. Let f be a differentiable function on an open interval I. The function f prime of x is called the derivative of f. So it's the derivative function, and it's exactly what you think it is. It's the limit as h goes to 0 of the difference quotient f of x plus h minus f of x, all divided by h. So the derivative function is this function, and I can plug in lots and lots of values. Once I find it, I can plug in lots and lots of values for x. Just as a note, the derivative function notation has lots and lots of different notations. We'll see why this is a little bit later in the semester, but the derivative function notation can be written as f prime of x. If my function of x is equal to some y value, then we can also say y prime. We can say dy over dx. What that means is the derivative of y with respect to the variable x, or the derivative of f with respect to the variable x, or the derivative with respect to variable x of f, or the derivative with respect to variable x of y. So there's lots and lots of different ways to write this. We'll see some reasons why we want multiple ways of writing this a little bit later. The one that we're going to see most often is the f prime or the y prime. So let's take the function that I'm used to seeing, x squared plus 3x minus 2, and let's find the derivative of that function. I'm going to go back and recall what we did to do the derivative of f at x equals -2. We plugged in a -2 into our difference quotient here. So for an arbitrary value of x, which is not -2, but just an arbitrary value, we plug in f prime of x is equal to f of arbitrary value of x plus h minus f of arbitrary value of x. Now you have to be careful here about how you plug things in, but from here on out, it's just a bunch of equivalent limits and a lot of algebraic manipulation. So when you plug in x plus h into the function, that means you're going to take this function here and replace every x you see with an x plus h. So I'm going to take that function and replace everywhere I see an x with an x plus h. And then I'm going to take the f of x, which I already know what that function looks like. f of x as an expression looks like x squared plus 3x minus 2. From here, it's a matter of simplification. I'm going to go through this fairly quickly. I hope that you can slow me down if I need to be slowed down, but the x plus h squared, when we do that, that's going to be x squared plus 2xh plus h squared. When I distribute the 3, I'm going to get 3x plus 3h. Over here, I can distribute a negative sign. So we're going to get negative x squared minus 3x plus 2. So take that. Now I can start combining like terms and simplifying. Because I distributed that negative sign, I can combine, I'm going to combine all the like terms on top. So the x squared and the minus x squared cancel each other out. We have a minus 2 and a plus 2 that cancel each other out. And I have a 3x and a minus 3x, which cancel each other out. So notice what we get here. We're getting an expression whose numerator is 2xh plus h squared plus 3h. Notice that everything in the numerator, by design, has an h in it. So what we can do is we can take that expression and divide each term in the numerator by h. I will end up with 2x plus h plus 3. Then I can finally plug in h of 0 because I don't have h in my denominator anymore. And so if you plug in an h of 0, you end up with 2x plus 3. So we just treat x as an arbitrary number, and we do our simplification over and over and over until you can finally plug in h of 0. Be careful here because we're plugging in an h value of 0 and not an x value of 0. So what this says is that the derivative of my function is 2x plus 3. Now let's compare that to what we found earlier. Remember what we found earlier was that the derivative of the function at -2 should have given me out a -1. Well, if I had known this earlier, I could have just plugged in the -2. 2 times -2 plus 3 does in fact give you a -1. If you were looking for the instantaneous rate of change when x was equal to 1, what I could have done is plugged in 2 times 1 plus 3. So I could have plugged in 1 into my derivative function, and I could have seen that that gave me out a 5. If you go back and look, the instantaneous rate of change when x was 1 was 5. The derivative when x was -2 was -1. And you can also do this for any other number. If I said, what's the derivative of f when x is 9, I can just plug in 9 into this. So 2 times 9 plus 3 is 21. And once I've done that mathematical operation of simplifying the difference quotient as the limit of h goes to, as the limit as h goes to 0, then I don't have to do anymore. I can just utilize this thing. And that saves me a lot of time if I'm trying to find lots and lots of derivatives of the same function. So we found the derivative of the function f of x equals x squared plus 3x minus 2. I want you to try to find the derivative of this function. G of x equals 3x squared minus 8. So go ahead, push pause on the video. On the next video, we will do this one.